Hey guys, this video is going to be about energy and heat. It is the first of the thermochemistry entry to thermodynamics videos. So here's some basic definitions of stuff that we're going to be using throughout this. System is the part of the universe that we're focusing our attention on. The surroundings is the rest of the universe. So system plus the surroundings is the universe. Exothermic, you should know what that is. Heat's released. It flows out of the system into the surroundings, and endothermic, heat is absorbed by the reaction, flows into the reaction from the surroundings. So the first law of thermodynamics is basically kind of like energy has to be conserved. It can't just disappear, and it can't come out of nowhere, so it has to flow from one place to another place. Internal energy, E, is the sum of all the kinetic and potential energies of a system. And it can be found by delta E is equal to the heat plus the work. We'll talk about that in a minute. And then state function. So state function is something that the route doesn't matter, like delta H. We've talked about that a little bit. We haven't really gone into any detail. We'll talk about it more in this video. We only look at the final position and the initial position. So it doesn't matter how it gets there, what happens in the middle of it, it's always going to be the same value. Whereas work matters. If I pick up a book and I walk all the way around the room and then put the book down 2 feet from where I started, I've expended a lot more work than if I just picked the book up and moved it over 2 feet. So work is not a state function because its value depends on its pathway. All right, so energy is the capacity to do work or produce heat. So remember the law of conservation of energy. Energy has to be constant. It can't change overall. Okay, it's usually measured in the units of joules or calories. Calories is really not used that much anymore in science that I see, but it's used a lot in food. We just use big calories, so those are actually kilocalories, but we don't really use that here. All right, so potential energy versus kinetic energy. Potential energy means that something has the potential to produce energy, and kinetic energy is the energy of motion. Heat, thermal energy, involves the transfer of energy due to a temperature difference. All right, so work is the force times the distance. All right, so let's look at this picture over here. All right, it says the energy change is the difference between the final and initial state. So the change in energy, that's a state function, is the final energy state minus the initial energy state. And so the surroundings, if this flask is inside of this box, the surroundings is the box, right? The flask, the solvent that the reaction is taking place in, and anything outside of the box is all the surroundings. The system is only the reaction itself. That's it. So when energy leaves the system and goes into the surroundings, so energy leaves the system and goes into the surroundings, the final state of the system has less energy than the initial state, and so the sign would be negative. And when energy goes into the system from the surroundings, so if it goes into the system from the surroundings, then the final state is greater than the initial state, and the sign will be positive. All right, so the overall energy of a system, delta E, is equal to Q plus W, okay? And it depends on both the heat and the work. So signs for heat, right? If heat is gained by the system, so it's coming from the surroundings to the system, it'd be positive. And if heat is lost by the system, then it's going to be negative. All right. And for work, if work is performed on the system by the surroundings, it's positive. And if work is performed by the system to the surroundings, then it's going to be negative. All right. And so here's the diagram. This bothers me a little bit, but that's the way I saw it in y'all's textbook. So that's the way I put it in here. If energy is leaving the system, then the delta E is less than 0, so it's exothermic because it's going to be negative. Its energy is being lost to the surroundings. And down here on the bottom, the energy is coming into the system from the surroundings, it's going to be positive, and so it's going to be endothermic. So a lot of the time students get confused about the system versus the surroundings. And we can't always measure the exact system. Sometimes we have to measure what's happening to the surroundings and know that it came from the system. So we'll look at that more in the next video, but just keep that in mind. Okay, so first example, calculate delta E for a system undergoing an endothermic process. So heat is positive, in which 15 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. So if work is done on the system, then work is going to be positive. So my Q is equal to positive 15.6 kilojoules, and my W is equal to plus 1.4 kilojoules. And delta E is what we're looking for, and that's Q plus W. So I'm just going to add those two numbers together, 15.6 plus 1.4, they're both in kilojoules, is 17.0 kilojoules. And the sign would be positive. All right, so pressure volume work. So a common way that work is performed by a chemical reaction is by gas expansion. All right, and when the reaction is carried out, it creates more gas, which expands and pushes up a piston. So I have this picture here, all right, and basically what's happening is something is happening inside of this, and this is where the piston started. And then it pushes it up because more gas is forming in here. So if there's something up here, right, a plate that has a block on it or whatever, it can push it up and move it and perform some sort of mechanical work. It's a lot of the way our cars work, the engine in the car. So now they put work out here. I got this from a physics OpenStax textbook, and they do things a little bit different than chemistry does, but it was the best one that I could find, so that's why I used it. But anyways, pressure is a force applied on a specific area. So if pressure equals force over area, we can rearrange that to where it's force, right? So we multiply both sides by area, and we get force is equal to pressure times area. And we also know that work is equal to force times distance. So if I substitute in pressure times area right here, then I get pressure times area times distance. Now, if we look at what's happening here, this is moving upward, right? And it's doing work on the surroundings because it's pushing against the surroundings. So therefore, this system is doing work on the surroundings, and when it does work on the surroundings, it becomes negative because it's losing that work. So we end up putting a negative sign here because we want it in terms of the system, not in terms of the surroundings. And if we take an area, a flat area, and we multiply it by height or distance, we get volume. And so that's where that comes from. And that's how this equation is derived. All right, and most of the time when we measure work or energy, we measure it in joules. Well, this isn't going to give us joules, it's going to give us liter ATM. So here's the conversion for that if you need it. All right, so example 2, calculate the work associated with the expansion, that's not an expansion, of a gas from 64 to 46 liters at a constant external pressure of 15 atm. So work is equal to negative P delta V. So delta V is the final minus the initial. Delta is always the last minus where it started. So final is going to be 46 and the initial is 64. So I'm going to take 46 minus 64, they're both in liters, that gives me 18 liters negative. So that's delta V. And then my pressure is 15 atm. So I'm going to plug those values in. So I have negative 15 atm times negative 18 liters. And that is going to give me 270 liter atm of work. Now, if I need this in joules, all I have to do is convert it. 1 liter atm times 101.325 joules. And that's going to give me positive 27.4 kilojoules. So 27.4 kilojoules was put into the system by the surroundings. Okay, the second one here, a balloon is being inflated to its full extent by heating the air inside it. In the final stages of this process, the volume of the balloon changes from 4 times 10 to the 6 liters to 4.5 times 10 to the 6 liters by the addition of 1.3 times 10 to the 8 joules of energy as heat. Assuming that the volume expands against a constant pressure of 1 atm, calculate the delta E for the process. So my initial volume is 4.00 times 10 to the 6 liters, and my final volume is 4.50 times 10 to the 6 liters. And I've got a positive heat because it's being added to the system in joules, and my pressure is equal to 1 atm. Now I want delta E, and I can get delta E by adding the heat plus the work, and I've got the heat right here, but I need the work, and so work can be found by taking negative P delta V. My work is going to be negative 1 atm, because it's this negative sign, times 4.50 times 10 to the 6th minus 4 times 10 to the 6th liters. And so when I put that in the calculator, what I end up getting out is 5 times 10 to the 5th liter atm. At this point, I have work and I have heat, but in order to add those two values together, they have to have the same units. So I have to convert my work to joules. So 1 liter atm is 101.325 joules. And that is going to give me negative 5.066 All right, enthalpy. Enthalpy is a state function which is defined as H is equal to E plus PV. But what exactly is enthalpy? Well, it's really hard to measure energy at a specific time. The change in energy is much easier to calculate. All right, so it's hard to describe what enthalpy is at a given point if we can't do energy. So what we know is if we consider constant pressure work, so pressure is not changing inside, the piston is allowed to expand. It's not stuck in a position like in a jar that has a lid that's screwed shut that could blow up if gas builds up in it, right? The pressure would be changing inside of it. So the pressure is allowed to stay the same. Gases are allowed to escape. Then we have this, right? And work is negative P delta V. And so if I switch this around, right, then I get that the heat at constant pressure, that's what this P means, that it's just constant pressure, is equal to delta E plus P delta V. And it doesn't have a delta P because pressure is being held constant. It's not changing. So that means that QP is equal to delta H because of that. All right, so as long as the pressure is allowed to stay constant, then the heat is equal to enthalpy, the change in enthalpy. Okay, so we're going to look at endothermic and exothermic a little bit closer and look at the difference between physical and chemical changes in terms of heat. So if we think about boiling water, don't think about if it's getting hot or cold. Think about what's happening to it. If we have liquid water and it's turning into gas water, these molecules have to absorb heat in order to do that. And so it's going to be endothermic. And our system here is the water. And the second one, solid zinc is added to HCl, H2 forms, and the temperature of the solution increases. So this is a chemical reaction, where the chemical reaction, the zinc and the HCl, is the system. The surroundings is the solution that it's sitting in. So since the temperature of the solution is getting bigger, that means the surroundings temperature is increasing, which means that this reaction is losing heat to its surroundings. So this is going to be exothermic. And our system here is not the water. It's not the solution. Our system is the reaction. So this up here is a physical change because the substance isn't changing. And this one down here is a chemical change. And so it's two different things that you have to think about. So next we have chlorine going to 2 chlorine atoms. And I put this on here because I think it's important to go over. Anytime you're breaking a bond, heat has to be put into it because you have to break something. So it's kind of like if you break a pencil, you have to put energy into it to break that pencil. So this is going to be endothermic. You have to put heat in. So the opposite is true when bonds are made. It's exothermic. It releases heat. Okay, so here we have a gas turning into a solid. And so if we have a bunch of crazy gas molecules flying all over the place, and they have to slow down and turn into a solid, they have to release energy to do that. So this is going to be exothermic. And our system here is the CO2. Number 5, when ammonium chloride is dissolved in water, the temperature of the water and resulting solution decreases. So we have NH4Cl dissociating into ammonium chloride. And then the water around it, the temperature goes down. So that means that this took heat in to dissolve. So this is going to be endothermic because our system is this reaction. Water vapor condensing on the surface of a cold soda can. So we have gas in the air and the coldness of the can, and because it's so cold, it condenses on the surface. So that means that those gas molecules have to lose heat to turn into a liquid. So it's going to be exothermic. And again, the water is the system. We have 1 mole of CH4 is burned at constant pressure. 890 kilojoules of heat is released as heat. Calculate delta H for a process in which 5.8 grams sample of methane is burned at constant pressure. All right, so we have CH4 plus O2 makes carbon dioxide and water vapor. All right, so anytime a hydrocarbon undergoes combustion, complete combustion, you always make carbon dioxide and water, and oxygen has to be a reactant. And we have 5.8 grams of methane. And when this reaction happens with 1 mole of methane, the delta H is equal to 890 kilojoules, and it's released. So we have to use the molar mass of methane because the relationship here is 1 mole of methane for 890 kilojoules. So it's 16.026 grams of methane is 1 mole. And then for every mole of methane, we have 890 kilojoules of heat released. So that release is negative 322 kilojoules. And then the next one, we have 47.2 grams of O2. I'm going to do the same thing, 32 grams of oxygen for every mole of oxygen. And then for 2 moles of oxygen, we release 890 kilojoules of heat because this value here is for this reaction the way that it's written. It says for every 1 mole of CH4, 2 moles of O2 burn to give us 1 mole of CO2 and 2 moles of water. And that will release this heat. So this heat is for 2 moles of oxygen. So we get negative 656 kilojoules of heat is released.